Similar solids. You've already seen that if the ratio of edge lengths of similar figures is a to b, then the ratio of areas of the figures will be a squared to b squared. Therefore, the one-dimensional ratio will get raised to the second power to compare areas. Or you can even refer to it as the scale factor getting raised to the second power. It is also true that the ratio of volumes of the figures will be a cubed to b cubed. If we move into three-dimensional space, the comparison of the ratio is now going to be to the third power, or you can say that the scale factor is now cubed. Example 1. This is going to be a little bit of a lengthy problem here. What we're going to do is investigate how the total surface area and the volume are affected if all the dimensions are multiplied by 2. Okay, and what we should see with respect to the introduction of the video here is that the total surface area is going to change by a factor of 4. That would be 2 squared. And the volume is going to change by a factor of 8, which is actually 2 cubed. Okay, now to figure all this out, we literally need to calculate the surface area and the volume of the figure. Okay, so let's start off with the surface area. We do have a rectangular prism, which has 3 pairs of congruent sides. You've got the bottom and the top that match with a dimension of 6 by 4. You got the left and the right, which match with dimensions of 4 and 14. You've got the front and the back, which have dimensions of 6 and 14. Okay, so the surface area of the rectangular prism can be calculated by taking 2 times the product of 6 and 4 plus 2 times the product of 4 and 14 and 2 times the product of 6 and 14. And most of this we can probably do as mental math. This is just 24 times 2, which is 48. 4 times 14 is going to give you 56. 56 times 2 is going to be 112. 6 times 14 times 2 will give you 168. Okay, and then if we take the total of all of that, we'll have the surface area of the figure before any changes on it. For that, I'm actually just going to type into the calculator. We're going to get 48 plus 112 plus 168, which gives us 328. Okay, that is the surface area without any dimension changes here. All right, so if we do change all the dimensions by a factor of 2, that'll give us a 12, an 8, and a 28. Okay, so changing things up here, we're going to have 2. We're still going to have 2 for the bottom and the top, but it's going to be 12 by 8. We're doubling those dimensions there. Okay. For the left and the right, it's going to be an 8 by 28. And for the front and the back, it's going to be 12 by 28. Okay, and then for that, I'm not going to do mental math. I'll just type all of it in, which is going to be 2 times 12 times 8 plus 2, let's use parentheses again, times 8 times 28 plus 2 times 12 and 28. Don't want to go there. Which is going to equal 1,312. Okay, and as you look at these two together, you might not notice much of a comparison. But the claim here is that because we're talking about area, if we change all of the dimensions by a factor of 2, the overall change to the surface area of the figure should be a factor of 4, which is going to be 2 to the second power. So if I take this answer and divide it by the 328, we get 4. The comparison is a factor of 4. All right, so for the volume, let's just divide this up here. For the volume, much easier calculation. As a rectangular prism, the volume is just going to be the product of all 3 dimensions. So 6 times 4 times 14 which again, I'll just use the calculator. 6 times 4 is 24, but times 14 is going to give us 336. That is the volume without any changes. With the changes, we're going to get 12 times 8 times 28. And before I even evaluate this, I want to show you that you can actually see the 2 cubed inside of this. You can see the 2 account for itself 3 times because of an easy comparison. You've got 6, you got 4, you got 14 originally. The 12 is actually just 6 times 2, so that accounts for one of your 2's. The 8 is going to be 2 times 4, so that's that second 2. Then 28 is going to be 2 times 14, which accounts for your third one. So the 2's are really just built in here. You can look at it as 2 times 6, 2 times 4, 2 times 14, and then that is your 2 cubed. Okay, but we'll go ahead and calculate. We're going to do 12 times 8 times 28, which gives us 2,688. And the claim is that if I divide that number by 336, I get what is 2 cubed, or 8. Example 2. The lateral surface areas of 2 similar cylinders are 1,019 centimeters squared and 425 centimeters squared. If the volume of the smaller cylinder is 1,157 centimeters cubed, what is the volume of the larger? Okay, so what we're really being provided with here are 2 values, the 1,019 and the 425, that relate the area. So we can actually figure out a scale factor that relates these 2 similar figures in 2 dimensions. What we're going to need to figure out is a scale factor that relates the figures in 3 dimensions so that we can get the volume of the larger one. Okay, so I'm going to draw a little table here just to organize my thoughts. We've got 3 different scale factors we can think about. We have a 1-dimensional scale factor, we have a 2-dimensional scale factor, and a 3-dimensional scale factor. So that would just be like length, this would be area, that would be volume. And we can actually figure out the 2D scale factor by simply dividing 1,019 by 425. Okay, so let's take a look at that. Okay, so this is the scale factor. It does not appear to be a nice number, but it is the scale factor that we have. Okay, so I'm going to go ahead and write it down as, let's call it we'll do 3 decimals, 397. The more that you take, the more accurate this will be. Okay, so what we need is the scale factor in 3D so that we can take the volume of the smaller cylinder and multiply by that factor to get the volume of the larger one. Okay, but we cannot go directly from here to there. What we're going to need to do is backtrack. We're going to go this direction. We're going to figure out what the 1-dimensional scale factor is by taking a square root. Once we have that number, we can then go this direction by raising to the 3rd power. Okay, and what I'm actually going to do is just build off of the number that I have in the calculator. Okay, so I'm going to take this and square root it. Okay, so I wrote it down as 3 decimals, but I'm actually going to square root the whole thing, which is going to give me this number. So we get 1.548. Okay, but I'm still going to keep that number in the calculator. All right, so I square rooted to get the 1-dimensional scale factor. If I cube that, I can get my 3-dimensional scale factor. Okay, so raise that to the 3rd power, and we get 3.712. Actually, that round up to a 3. Okay, so we get 3.713. So that we can use to multiply by the volume of the smaller figure. So we'll take 1157 times 3.713, and that will give us our answer. Of course, I can continue to build off of the actual value for this. Just take what I've got, multiply that by 1157, and that's it. The volume of the larger figure is 4,295, we'll say 0.5. Units will be centimeters cubed. That is a volume. And last, I'm going to show you an example of non-proportional changes. What that means is that the dimensions of the figure are not all changing by the same amount. We're not doubling all the dimensions, we're not tripling all the dimensions, we're not cutting them all in half. What we're doing is changing each of the dimensions by a different amount. In this example, we're going to look at the total surface area and the volume when the cylinder has the height tripled and the radius doubled. Okay, so the dimensions aren't changing by the same amount. We've got the height being tripled, the radius being doubled here. Okay, let's go ahead and start off with some formulas though. For the surface area, that would be 2 circles, so 2 pi r squared, plus the wrapping part, which is circumference times height, so that'll be 2 pi r times h. The volume is going to be equal to the area of the base, which is the circle, pi r squared, times the height. Okay, so let's calculate these with the dimensions that we have. We've got 2 times pi times 4 squared plus 2 times pi times 4 times 12. For the volume, that'll be pi times 4 squared times 12. Now, some of this can be done in mental math. And in fact, I'm going to keep everything in terms of pi, because in a little while, what we're going to do is take the new surface area and the new volume and divide those by the old surface area and the old volume. Okay, so by leaving it in terms of pi, it should make the numbers look a little bit better. All right, now calculating these, we have 16 times 2, which is 32. So I'm going to call that 32 pi. Over here, I've got 2 times 4, which is 8. 8 times 12 is going to be 96. And 32 plus 96 is 128. So we'll call that 128 pi. For the volume, we're looking at 16 times 12, which is 192. All right, so now let's calculate the surface area and the volume with the changes. Okay, we're going to double the radius to an 8. We're going to triple the height to a 36. So we're going to have 2 times pi times 8 squared plus 2 times pi times 8 times 36. Okay, the radius is doubled to 8. The height is now 36. For the volume, that's going to be 8 squared times 36. All right, so this is probably out of my mental math range, so I'm just going to type it in. We're going to get 2 times 8 squared, so that's 64, plus 2 times 8 times 36, which is going to give us 704 pi. Okay, and then for our volume, we're looking at 64 times 36, which is going to give us 2,304 pi. Okay, and then to compare the changes, what I'm going to do is take 704 and divide that by 128, which gives us 5.5. Okay, so the pi's here would have canceled with the division, so I don't really need to worry about that. The change that we're going to get is 5.5. We'll just write 5.5 change. And that's like a scale factor change. Okay, and then for the volume, we're going to take 2,304, divide that by 192, and get 12. So we're going to get a change as a factor of 12. All right, I want to show you one more thing here. The change in the volume can actually be figured out without actually having a picture with certain values in it. Okay, the volume formula for the cylinder was pi r squared times h. Okay, and the reason this is going to work is because the volume formula is literally just a product of a bunch of numbers. What I'm about to demonstrate here does not apply to surface area because our approach at surface area is to break that into a lot of parts and then add them together. But because this is a complete product, we can actually use this as maybe a trick. Okay, now when we change the dimensions, the radius gets doubled and the height gets tripled. Okay, so what I'm going to do is substitute in for the radius, substitute in for the r, 2r, double the radius, and substitute in for the h, 3h, which is triple the height. Okay, now with a little bit of algebra, I'm going to go ahead and square that, which is going to give us 4r squared. This is still 3h. Then group all the numerical factors together, which would be the 4 and the 3. So 4 times 3 is going to give you 12. You still got the pi, you still got r squared, you also got h. And this is the original formula. So with the changes that we have here, the tripled height and the doubled radius, the overall change is a factor of 12, which is the same thing that we got when we calculated the volume with these numbers and then those numbers doubled and tripled.
Lateral.